right, people, we're going to be doing some enthalpy of formation problems. Now, the first one we're going to start off with is pretty simple, but the second one's going to be a little bit more work. Okay, but it's the same concept. It's just bigger numbers and an extra step or two extra steps. All right, but let's check out this one right here. It's a good example. We're looking at the enthalpy change during the thermite reaction. All right, so before we even start that, I want you to remember how things in their atom form, their elemental form, they do not have, or their value is zero for their enthalpy of formation. So this is going to be 0 and this is going to be 0. So the only really thing we're going to be focusing on is the compounds. So with that in mind, let's go and let's get started. Now, we always use this formula, and remember that delta is always final minus initial, but in this case, it's products minus reactants, so last minus first. And the products we are focusing on is Al2O3. There's only 1 mole of it there, so it's 1 mole times the delta H F value, the enthalpy of formation of Al2O3, which is negative 1,676, and the units are kJ per mole. All right. I believe they're actually just kJ. Let me double check. Table 6.2. I gotta double check. Yeah. All right. So the next thing, the reactant side. We have 1 mole of Fe2O3. I'm gonna write it in red so that we can use it as a, I don't know, it just kind of stands out a little bit more. The Fe2O3 value is negative 826 kilojoules per mole. And if we do a little bit of this math, negative 1,676. So negative 1,676, and this is a negative times a negative, so that's going to be a positive. So we're going to add 826, and the delta H value is negative 850 kilojoules per mole. The reason it's per mole is because these are 1 mole. All right. So that's our answer here. That's it. Boom. You're done. Finished. But let's check out problem number 2. Now, in problem number 2, I wrote some stuff out just for the sake of time because this problem is a little bit longer. So let's kind of check it out. Methanol is often used as a fuel in a high-performance engine in race cars. Using the data in table 6.2, compare the standard enthalpy of combustion per gram. So enthalpy of combustion, stuff we've been doing, but then these jerks went on and added per gram, all right, of methanol with that of per gram of gasoline. Ugh, more work. How unfortunate for us. It says gasoline is actually a mixture of compounds, but for this problem, let's assume gasoline is pure liquid octane. All right, now, give me 1 second. My wife's going to show up in just a moment. She's going to be knocking on the door. It's going to be loud. All right, so what have I done? Well, let's take a look. Remember that our delta H is products minus reactants. So the product is 4H2O, so I have the 4 here, and I have the value of H2O written out. There's 2 CO2s, so I write down 2 times that value right there. Now I subtract and I check the reactant side. The reactants, I have 2 methanols and 3 oxygens, but I don't include oxygens. I don't include the oxygens because they are in their elemental state. So the value for it is 0, so I don't bother writing it out. Now, once we have all this written out, we are ready to actually solve for this. So 4 times 286, but negative. It's a negative 1,144. But kJ. I don't think this is per mole because there's two of them, but whatever. Oh, the moles cancel. That's what happens. The moles cancel because this is 4 moles times that. I was wondering what I was doing wrong. The moles cancel. I didn't show that in my last problem. That's slightly incorrect on my behalf. 2 times 394. So that's negative 788 kilojoules. So the moles cancel because this is 2 moles, and then the units will cancel there. So right here, 239 times 2. This one I'm not bothering with the negative sign because I know negative times a negative is a positive. And now we are able to find our delta H. So let's go ahead and do that. Just finish up the work right here. And we get negative 1,454 kilojoules. Now, this is how many kilojoules are released from 2 moles of methanol. So 2 moles of methanol release that. Keep that in mind, because what we want to do is figure out the per gram amount. Since there's 2 moles of methanol, we got to divide by 2 times the molar mass. So 2 times the molar mass. Why? Because there's 2 methanols, and the molar mass of methanol is 32.04. I had a mistake up here. I had it as 32.0. But so there we have it. Let's find let's find the actual value. So negative 1,454 divided by 64.08, and that gives us a value of negative 22.69 kilojoules per gram. And then this is per gram of CH3OH. All right. So if you have 1 gram of methanol, it can release that much energy. Pretty nice. Now let's go and let's compare. Let's go and compare. Is that the correct value? That should be. Yeah, it is. All right. Let's go and compare gasoline. And gasoline, I already had the problem mostly set up. I just didn't finish it. But let's look at the products minus the reactant. So there was 18 waters. There was 16 CO2s. So let's look at the value for CO2. That's negative 394. I'll write it in a different color. Negative 394. And I'm just going to write kilojoules because the moles are going to cancel. The 18 for water, well, that was negative 286 kilojoules. Oof, that's hideous looking, huh? All right, I'll write it a little neater so you won't say anything. You'll be like, oh, what's he writing? He's writing all this. I said a little neater, okay? Not super neat. Now, for this one is negative 269. And we're just writing kilojoules. It should say kilojoules per mole, and the moles should cancel. But let's just try to keep things simple, okay? So 16 times 394. Well, that was a negative 6,304 kJ. And this 18 times 286, but that's negative, so it's a negative. So we're going to change that plus to a minus. And it is 5,148 kilojoules. And then over here, negative times a negative is a positive. So 269 times 2 is 538 kilojoules. Now, if we add these all up, so minus 5,448 minus 6,304, we get a negative 10,914 kilojoules. Now, the same thing, remember, we are looking at octane, And octane has a molar mass of 142. But there are two of them because this much heat is produced from 2 moles of that. And we don't want to do it per 2 moles. We want to do it per gram. So what we do is we divide by 2 times the molar mass because it's 2 moles. So divided by 2 times 114.2. So if you divide negative 10,914 by 228.4, you'll get a value of negative 47.78 kilojoules per gram. So that is of octane, C8H18, and we're going to compare it with methanol. All right, so obviously octane can produce a significant more, release a significant more. Can't talk. It releases way more heat, like twice the amount. And that's kind of it. That's kind of it for this problem. That's it. That's a long problem, huh? Oof. It's a little bit of a doozy, but as long as you stay organized and as long as you continue to read what the problem says, be aware of the per gram, stay organized, check your coefficients. When it says per gram, consider how many moles you had to begin with to help you determine what you divide with in these scenarios, okay? Well, I'll see you later. I believe this is going to cover the chapter. We're done with chapter 6. Woo! Well, you got practice problems and tests and stuff, but I'm done.